Welcome to Higher Degree Polynomial Characteristics. The best way to use this video is to watch with your notebook and take notes while I'm teaching. Pause the video often to get the notes down. Every time the video arrives at a "you try," pause and attempt the problem. The solution will be shown along with the work. In this section, we're going to cover the following topics. Higher degree polynomials are functions that have the form f of x equals and the degree of the function is greater than 2. There are two general forms of looking at higher degree polynomial functions: factored form and general form. When we're looking at factored form and we want to find the degree of a polynomial function, we add up all of the exponents. So for example, if we're given this function here, the degree would be 3 plus 2, the degree would be 5. But in general form, we simply take the highest degree. So in this function here, it's written in general form. The highest exponent is 3, so the degree is 3. We'll do two examples. What is the degree of each function? So first, decide if it's in general form or factored form. This is in factored form, and there's an invisible exponent of a 1. To find the degree, we're going to add the exponents. We would get 2 plus 1 plus 5. The degree is 8. Ask yourself, is g of x in general form or factored form? This is in general form, so we find the highest exponent. I got tricked right there. The degree of this function is 7. You tried these two examples. Press play when you're ready to see the answers. Great. Now we're going to talk about end behavior of a polynomial function. End behavior is determined by two things: the leading coefficient, and whether it's positive or negative, as well as the degree of the function and whether it's even or odd. So take a look at this chart. If you have a positive leading coefficient and you have an even degree, then the ends of the graph are going to look something like this. If you have a positive leading coefficient, but you've got an odd degree, it's going to look something like this. And if you've got a negative leading coefficient, but an even degree, it's going to be pointing both down, an odd degree pointing this way and that way. You can remember that odd degrees point in opposite directions. So let's describe the end behavior of the functions. So first we need to see, are these in standard form? Let's rewrite them from highest degree to lowest degree. We'll rewrite the first one. It's not necessary to rewrite them, but we are looking for that leading term. So the degree with the highest exponent. So our degree in this case would be 9. So that's odd. And our leading coefficient is -10, so we have a negative leading coefficient, which means the end behavior is going to look something like that. Let's take a look at this function here. This term would go first if I was to rewrite it in standard form. The degree is 6, so that's even. The leading coefficient is 5, that's positive, so the end behavior is going to look something like that. You try these two examples. Based on the graphs, determine the type of leading coefficient, positive or negative, and the degree the function would have. So first find the ends of this graph. So the ends of this graph, it's going down this way and up this way. So the ends of the graph look like this. Well, it's definitely an odd degree because they're going in opposite directions. And because it's pointing up, we've got that leading coefficient is positive. Let's take a look at this one here. Our end behavior, they're both pointing down. Because they're both pointing in the same direction, we've got an even degree. And because they're pointing down, we know our leading coefficient is negative. You try with these three examples. See how you did. Now we're going to talk about turning points. Turning points are the points on the graph where the graph changes from increasing to decreasing or decreasing to increasing. For example, this graph has two turning points. It was increasing, now it's decreasing. It was decreasing, now it's increasing. A polynomial of degree n will have at most n minus 1 turning points. It doesn't have to have n minus 1 turning points, but that's the most amount. What is the maximum number of turning points the graph could have? To determine turning points, we need the degree. And then if the degree is n, we've got n minus 1 turning points. So let's find the degree of this function. The degree is 9, so it can have a maximum of 8 turning points. The degree of this function is 6, so it can have a maximum of 5 turning points. Again, it doesn't have to have all 5, but it does have the option to have 5. Zeros of a polynomial function. This is one of the most important things. The zeros of a polynomial function are still those x-intercepts or roots. A polynomial of degree n has at most n zeros. That's the maximum number of zeros. Without graphing the function, find the maximum number of x-intercepts and turning points. All right, so both of those have to do with the degree. So the degree in this case is 10. So if the degree is 10, it has a maximum of 9 turning points and a maximum of 10 zeros. You try this example on your own. See how you did. We're going to continue to talk about the zeros. If a function is written in factored form, you can find the zeros by setting each factor equal to 0 and solving. If the function is graphed, you can find the real zeros by looking at where the graph crosses the x-axis. Note, there are non-real zeros. You found those in the quadratic formula. We are not capable of seeing imaginary things, so we can't see imaginary zeros. Example 5, find the zeros of the polynomial function. So these are both written, f of x and g of x, in factored form. So we set each factor equal to 0. So x plus 2 equals 0, x plus 1 equals 0, and x minus 1 equals 0. So the zeros are x equals negative 2, x equals negative 1, and x equals 1. I want you to notice the relationship between the 0 and the factor. The factor was plus 2, the 0 is minus 2. The factor here was plus 1, the 0 is minus 1. And the factor here was minus 1, and the answer is plus 1. So maybe without showing any work here, see if you can figure these two out. I'll explain that one in a moment. So we know that the factor is minus 2, so the 0 has to be positive 2. We know that the factor is plus 4, so the 0 has to be negative 4. Let's take a look at this. This is x. So we want to know where x is 0. Well, that factor is simply x equals 0. You try these two examples on your own and see how you did. Each zero has a multiplicity. The multiplicity is the number of times that associated factor appears in the function. And the thing about multiplicity is it determines the behavior of the graph at the function. We'll talk about that more in a minute. So looking at this example of this function, the 0 is negative 1, but it's got a multiplicity of 2 because of that exponent. So what does the multiplicity mean? Well, if you have an odd multiplicity, the graph will cross at the x-intercept. So let's say you've got a multiplicity of negative 3, and the graph was coming down here, it will cross. If you have an even multiplicity, the graph will bounce back at that 0. So let's say you're looking at that negative 3, the graph was coming up, and it bounces back down. So looking at these examples, the multiplicity here is 5. So 5 is odd, which means the graph will cross. Here the multiplicity is 4. That's even, so the graph will bounce. So let's just take a look at bouncing and crossing. This graph hits at a single 0, and it is crossing the x-axis. This 0 here has a multiplicity of 2, So it is bouncing back up because 2 is even. And this 0 has a multiplicity of 3, which means it's going to cross because it is odd. So we're going to determine the zeros, the multiplicity, and the behavior. So the factor is +2, 0 is -2, +1, the 0 is -1, and -1, the 0 is +1. What is the multiplicity? The multiplicity for this is 4. The multiplicity for this 0 is 5. The multiplicity for this 0, it's not 0, it's an imaginary 1. So what's going to happen at each of these? So if the multiplicity is even, so maybe you go through and label odd, odd. So even is bounce and odds are cross. Okay, let's try another. So finding your zeros, our zeros are x equals 0, x equals 2, x equals -4. And let's go through and do the multiplicity. Well, the multiplicity for this 0 is 2. The multiplicity here is 3. And the multiplicity here is 5. So this is an even multiplicity, that's an odd multiplicity and an odd multiplicity, so it's going to bounce, cross, and cross. All right, you're going to try this example here and see how you did. And our last vocabulary is the maximums and the minimums. An absolute minimum is the point on the graph which has the smallest value of y. So no matter what's happening on this graph, the absolute minimum is that lowest point. And an absolute maximum is the point that has the largest value. So no matter how many peaks we've got, it's the biggest peak we can see here. So now we're going to talk about the relative maximum and minimum. So relative just means it's relatively the smallest according to the ones around it. So if we've got those kind of peaks here, our relative minimums are all of those valleys. That they're not the lowest, that's the absolute, but these guys here are the relative minimums. And then the relative maximums are those mountain peaks. No matter how high those mountains are, this might not be the highest, but it's still a peak for the areas around it. So these are the relatives, whereas that's the absolute. Another image here to help you. And we'll do our last example together. Identify any absolute and relative maximums and minimums. So I'm always looking for the peaks and the valleys. So I'm just going to go through and put dots at all those high points and low points. And then I've got arrows here. So this is a minimum, I know that, and this is a minimum. So which of these is the most? Well, this guy here. So this would just be a relative. And then let's look at our maximums. Well, this is a maximum, our arrows here, and this is a maximum. So which is the biggest? Well, our absolute maximum is going to be infinity, so this is our relative maximum. This next one here, we've got an arrow going down and an arrow going up. So this is going to be a low point. There's a point, there's a point, there's a point down here. So let's go through and label. We've got, this is a minimum because it's pointing down, and this is a minimum. Well, this is going down forever, so that's the absolute, and here's the relative. And here's a minimum here, and that's a relative. We've got maximum, maximum, and maximum. This guy's going up forever, so he's the absolute, so these are our relatives. And that concludes higher degree polynomial characteristics.